Welcome to my talk about testing with hypotheses. So, quick information up front. Actually, this talk was a talk I held at the Python SaarPython Meetup number 6 in August 2022. Unfortunately, the live screen recording broke, so there's no audience now. I'm recording this just live for video on demand here. And yeah, I hope that the experience will be roughly the same. You just need to imagine a few laughters here and there. So anyways, and maybe I'll even remember some of the questions that have been asked in the end and can go into these as well. So let's start and hope that the recording works this time. Okay, so this is the topic, as I said, testing with hypotheses, which is a Python topic, and the handy short title, how to make your code more robust and maintainable with automated fuzzing, already kind of hints at, we're going to talk about testing today. Who am I? My name is Sebastian. I like coffee, usually a lot of it with milk, no sugar. I like bouldering. I love Python programming. It's an awesome language. And I work at that company that actually sponsored the 6th Python SaarPython Meetup this time. And by the way, this is actually me. And I don't wanna keep back the joke that I did at this point to the audience, which is in a group of people, how do you recognize who of these are the boulderers in the room? It's that easy. You just wait for them to tell you, because we're usually proud of it. Okay, flat jokes aside, let's dive right into the topic. So I said this is gonna be a testing talk in Python. So there are a few questions that come naturally to you when you start thinking about testing, maybe initially or maybe even later on when you're already a tester, so to say. First one is, why should you even test? And honestly, this is not the focus of this talk. I would say we just pretend for a few minutes that we're all civilized people and we know that we need to test code that is going to end up on production. We want our software to be robust, we want less bugs, and we don't want to break anything that we've written in the future if we change anything about it. So tests are important, just believe me. Second question would be, what should you test? And there is this recent concept called the testing trophy. Maybe you've heard about it. It's similar to the testing triangle or testing pyramid that is more popular, I think. I don't remember exactly who coined it, but it was published via Twitter. And the main idea is that you have a foundation of static tests, tests that don't even execute your code. They just look at the code and things like code formatters, import sorters, type checkers, code linters. These are static checks. They run a lot and they run fast. Then above that you have unit tests, the small bits and pieces of your software. They are tested in isolation if they're doing the right thing. Then on top of that you have integration tests, testing how the small bits and pieces go together and how they interact with each other and if they do so correctly. And all on the top you have end-to-end tests where you can test entire customer journeys or whole features, the whole slice, how the whole system actually behaves in the end. And the idea is that you should write not too many tests and mostly integration tests, because they are kind of quick wins for the behavior of the whole system. End-to-end tests are where the actual money is made. This is close to the customer. They use the software from this side. While on the bottom, that's where we as developers live. We type a few letters in our IDE and we want to see immediately if we broke something, like first with static tests, maybe with code completion, type hints and so on, but then also unit tests, like we want to execute them regularly and quickly. And this is actually where this talk is going to live, like in the unit test section, maybe going a bit into the integration up to end, but like this it's mainly in the unit testing area. So third question would be how to test. And I'm just gonna assume that for most of us developers, the testing experience is usually somewhat like this. Like, we actually care about the production code, about the code that solves the problem at hand, not so much about the testing code. We do it because we recognize that it's like kind of important to write your tests, but we don't really think about like what exactly should we test and how does it work. We just do it until there's like a point where we're kind of confident that it tests the right thing and the tests are green. And actually I forgot to fix something about this meme. Most of us, I think, actually hate writing the tests. Like, it feels like a burden to do that. And like usually I imagine most of us, including me, we write tests or used to write tests a bit like this. There's this scheme for tests called given when then, and it reads something like this: given some preconditions, when I execute my functionality, then the output should be what I expect. And the small footnotes here are these preconditions. I actually have to come up with them by hand. Like, I need to know what potential inputs to my functionality could be, what the potential system state before my execution could be. Like, my imagination here, like I come up with stuff that I initialize, then I execute my functionality, and whatever comes out of my functionality is usually kind of based on my in-brain built-in Python interpreter. Like, I take the inputs, I know what my function is supposed to do, and I kind of work out what at execution time it would produce so that I know what I can compare the result with. This is example-based testing. And it kind of makes sense. But let's look at some code and I'll show you something. So I have written a function, it's called mySort1, which should be a little hint at what it's supposed to do. Actually, if we have a look at it, like maybe you recognize this. Of course, it's a quick sort. Yeah, we have the pivot, we partition, and we recurse. Why quick sort? Because why not? I mean, Python does have a standard implementation, standard library sort function, but it's just fun to write your own sort, right? So I did that. Anyways, I need to find the shortcut to go back, right? And here's a test for that function. We have an example. It's 132, a list of 3 numbers that are not in order. And what do we expect that to produce, that sort function? Naturally, like the sorted version of that list, 1, 2, 3. And if we actually run that, nice, the test passes, right? So job done. Not quite. Maybe you think like just one example, that's a bit too few. Maybe we should expand and like luckily PyTest got our back. Like, there's this nice functionality that you can write a test once and then run it with multiple examples automatically. And yeah, so let's do so. Let's have a few more test examples, like 1, 2, 3, the list is already sorted, or like the example we had before, 3, 2, 1, maybe a few other numbers like 6, 5, 4, maybe even an empty list. Like, let's try all of these. And luckily, our function still works. Maybe now we think like, okay, these are happy paths. Maybe our function should also be able to kind of cope with nonsense data, or at least we don't want it to crash unexpectedly. So what do we think could happen? Well, if we try to compare something that isn't comparable, like for example an integer with a null value, or an integer with a string, or an integer with a list, or whatever, like we expect that this may erase a type error, but we don't expect anything else than a type error. And in particular, we don't expect the function to succeed then. So let's try if like our test function fulfills this. And actually it does. Awesome. So I guess we're done now with testing, right? Well, let's see. I've prepared a different implementation of my sort. And if we run the test suite on this alternative implementation, actually, all of my tests still pass. But if we have a look at what this function actually does, it isn't even a sort. It's just a lookup table that takes the sum of the input sequence and then looks up what it should return based on this. And seems like my fantasy, like my imagination, my imaginary power to come up with good examples for testing the thing was not sufficient to figure this out. I mean, and like clearly you can already see that no matter how many examples I put into a function, it's always possible to implement a function that is just a lookup table to fulfill this test, like unless you're dealing with a lot of side effects and stuff. But yeah, so, and there's also my sort 3, and if we run the tests, like they still pass. What now? And my sort 3, I mean, you guessed it, it's also not really a sort function. It just takes the minimum element of whatever it gets and just returns a range counting up from that minimum value until it reaches the original length. So if we have a look at our examples, oh wait, wrong shortcut, then we realize that like actually this is what people actually tend to do. We came up with very simple examples actually. Like if I had tested here lists with steps between the numbers greater than 1, it would have appeared that like this is not actually a sort function, but we didn't, because like you actually need to come up with these edge cases. So I could go on and on. Like it's not really possible to test if a function is actually what it should be, just that it behaves like we wrote the tests, basically. So let's go back to the presentation. What if I now told you that there's a completely different approach to testing that kind of gets this out of the way? And it's called property-based testing. You recognize the given when then scheme, but now it's modified a bit, and conveniently I highlighted the changed parts, like the essential parts, in red. Given all possible inputs, when I execute my functionality, then the fundamental properties of my algorithm hold true. And the explanation is like, okay, fundamental properties, I'll go into what that means in a second. But basically it's like how I think my functionality is supposed to behave in general. Given all possible inputs, well, maybe that makes sense mathematically, but in reality, like enumerating all of something is like, or infinitely many, is not possible, but at least we can do a lot of arbitrary inputs. Like arbitrarily many, I mean. And what are fundamental properties of a sort algorithm now, you could ask. And I've listed some of these here. Like, for example, if I have a sort algorithm, it's usually deterministic. Like, if I put something in, then no matter when and how often I do this, the result would always be the same. Like, it only depends on the input, what comes out of it. I'm not going to try and pronounce this in English. I think I can't. But like doing sorting multiple times stops changing anything. Like if I sort it once and sort the sorted thing again, then the order doesn't change anymore. length invariance between input and output. Like if I put in a list that has length 6, say, then a list of length 6 comes out of it. Then, I mean, if a whole list is sorted, a whole sequence is sorted, then each individual neighboring pair is also sorted. And things like this can easily be tested. Or like if I take the minimum element of the sorted result, then it should end up in first place, and so forth. Often these are invariants that like stay the same between input and output when I execute my functionality. So look at this beauty. This is how a test could look like. In this case, like I take some example data, I sort it once, I sort the already sorted thing again, and then I compare that sorting once results in the same thing as sorting it twice. And like I don't at all have to deal with what is actually the input data, what's the output data. I just assume I have some input data that is valid, like wherever it comes from, and then fundamental properties based on the input data and the algorithm hold true. This is beautiful, I think. So like the small little detail here is this sample data that we just assume to be magically there. Where do we actually get that from? Like how do we generate all possible inputs? Like where's our that's a problem here. But luckily we have Hypothesis, which is a smart little Python library that we can just pip install or poetry install if you prefer, like I prefer, that can actually help us doing this. Hypothesis is a library that can run each of your tests many times with generated input data, a bit similar to PyTest parameterize that I showed you before. It's that easy to use. You have just a decorator called given, and for some input parameter of your test function, it takes a data generation strategy that it will use to create test data for you. And like you may recognize from the given when then scheme that this actually takes care of the given step entirely, and you only have to do the when and then. It's not generating input data entirely random, but actually does a systematic search through the space of input data, depending on which strategies you actually use. And it comes with many built-in strategies to generate data, like simple numbers or booleans or nuns, but also more complex data. We'll go into that later. On failure, it doesn't actually just flag that it found input data that failed the test, but actually it even does a search and tries to minimize the failing examples until it found the minimal example that still makes the test red, which makes it much easier to find the underlying issue. And it even does some additional health checks on how your tests are written, like are they taking too long, do they have flaky results, like they pass sometimes but fail some other times, more or less randomly. These flaky tests are really annoying, and Hypothesis kind of cleverly tries to detect that and flag if it's true. Things like this. So, coding time again. Let's have a look at some more code. So if I go to my alternative test file now, still the same sorting algorithm, but now look at these tests. I test the deterministic property, like I sort something once and the same thing a second time, and the result should be the same. Same for if I sort something twice, it should stay the same. I've already shown this on the slides. Or I test the length invariance. Like I have an example sequence, I sort it, the length should stay the same between input and output. Or maybe I want to assert something on the data types, like I put a sequence in and whatever I get out should be a list. Or maybe, if I prefer, it should be iterable somehow. Or consecutive pairs in the resulting sorted list, they are actually sorted, like they are in the right order. Things like this, like you just test the fundamental properties of what you think a sort algorithm should actually obey, and you use this given decorator. In this case, I let my parameter sample be populated with a strategy that produces lists. And since lists is a composite data type, it actually takes a child strategy that tells it how to generate the elements, which in this case is integers. So technically I only test my sorting function for lists of integers, but like fine for the toy example here. So let's run the test suite. Nice, my actual quicksort implementation seems to be correct with respect to these property-based tests. Let's try one of the fake ones. Seems like my lookup table actually obeys many of these, but like the length invariance is clearly wrong here. And hypothesis, like if I have a look at the detailed output, it actually tells me what the falsifying example is. If I input a list with just a 0 in it into my function, then this is the minimal example hypothesis could find to actually make this test fail. I got an empty list back, should have gotten a list with a 0 back. Yeah, so now I can take this minimal failing example and now use my brain-based interpreter to actually work out why this failed, but not already during testing time. So let's check the third fake implementation, and maybe I've spoiled that here a bit. Like if I execute now, oh wait, this passes all the tests, and like turns out that I forgot to test a very important property that sorting algorithms should have, which is they shouldn't change what's in the original list. Like we've tested a lot of interesting properties, but we forgot about these two. It should preserve the values that I give in, and it shouldn't come up with new values. So only if I complete my test suite to this, I can actually flag that my third fake function is not a sort in this sense. So this is a word of warning already. Property-based testing is not a silver bullet. It's an additional approach, and I think it's an awesome additional approach to testing. And it helps you think about testing in a different way. But you need to be very careful if you test like this, because it's really easy to just forget about very essential properties of your algorithm and not test these at all and call it a day, and then in the end you open the door for bugs. So if I go back to the presentation now, let's discuss this issue. Isn't this just example-based testing in disguise? Like, still need to think about how to write my tests correctly. And it just tests a lot of inputs, like examples basically. Kind of, yeah, but first of all, like if not you come up with testing examples, but actually the machine does, you can systematically explore edge cases that you didn't even think of. Like this systematic automated search, it's way more creative than you are. Just like let's not think that we as humans are good at creating random data. We are not. And if you don't find these edge cases, then you can be certain that in production your users will. Like users always find bugs. Production software always has bugs, and they are always uncovered. Like probably like up to now you have heard of Hiram's law. Not gonna cite it exactly here, but essentially it says something along the lines of whatever observable behavior your function has, whether it's documented or not, someone will eventually depend on it. Like if you have a bug in your software and someone finds out, then may well be that they integrate it like this in their system, and if you fix the bug afterwards, it breaks their workflow. Like you can't do anything against it. So you should prevent bugs in the first place. And it makes you think a lot harder about your design. Like example-based testing doesn't really force you to do that, because you can always come up with examples and outputs, but when you have to think about fundamental properties of what you're actually trying to solve, this, in my experience, actually tends to lead to better design of your function, like single responsibilities and less side effects and so on. Like if you have a function that is well testable in a property-based way, it's usually at a good abstraction level and well designed. Yeah, and if it's easy for a functionality to actually find out what its properties should be, then probably it's doing the right thing, right? And not too much. So coding time again. Let's see what hypothesis can actually do. And to do that, I actually have another test suite. Test hypothesis behavior. And these are not actually tests. I just wrote it as tests because it's convenient. This here just prints out what hypothesis actually generates. And if we have a look here, like I have showcased some stuff here. Number will be a parameter that where we put in numeric values, so to say. And it shows that you can combine strategies together. Like in this case, if you logically, if you OR different strategies together, then hypothesis will actually combine these to make a selection between these each time. Like this overall strategy may generate integers or floats or booleans. Same here, we have a composite type. We generate lists, and the elements of the lists could be sampled from this input list, so either foo or bar, or a none. Or we have a strategy that generates strings, but only to a maximum size of 10. And like usually all of these built-in strategies are kind of parameterizable for min values, max values, or for lists, for example, unique entries can be enforced and so on. So if we have a look at what this actually generates, then we see hypothesis starts slowly. It starts with simple examples like zeros, true, false, empty lists, empty strings, strings with a single value in them. That could be an integer as well, stuff like this. But it escalates quickly, actually. Here already we have a string with really weird Unicode characters, still valid Unicode characters though. And the numbers grow really fast. Like here we already have a very low floating point number. Here a massively low floating point number. Long lists with a lot of nuns, even more weird character strings, and so on. It goes on and on and on and on. It retries a few simpler examples. It does stuff twice. Until it finally like gives up and is satisfied and says, okay, I've tested enough this function, I now trust it that it doesn't fail. So let's have a look at what actually happens if a test would fail. In this test case, I've simulated that a functionality would fail whenever there's a uppercase letter A in the input string. So let's see what happens here. Oh, and hopefully I've deleted my hypothesis cache. Let's see. Anyways, we'll see what happens anyways in this case. So if I had deleted my hypothesis cache, then we would have seen that hypothesis actually takes some time to systematically generate a string that actually contains an A. But as soon as it recognizes that there is a failing example, it will not stop there. It will actually try a few more input examples and try and break down if it can simplify this. Like first, like the strings grow and grow and grow, still failing. Oh, if I just try a single A, it's failing. If I try a few other strings, it's not failing anymore. And like in the end, it actually comes up with the hypothesis that just a string with a single A might be the smallest example that you can actually come up with that makes this test fail. Maybe we can, I mean, I'm not under time pressure here because I'm not live anymore, so why not just delete the hypothesis cache for once and see it in action actually, what it really does if it doesn't have the failing example already in its memory. Yeah, here we see that it starts out simple again, then the strings grow, blah blah blah, and at some point occasionally it will find an example where there's an uppercase A included. Oh, here. I think this may be the first occurrence of a failing test, and we see there's an uppercase A here. So now the search will begin, and it will try kind of a sophisticated binary search to break down this example more and more until it ends up with the same hypothesis. Probably a string with a single uppercase A is actually your minimal failing example. Now you can go and search for a bug, and like this is actually the bug in this case, and it's actually pretty common that hypothesis finds the bug in the first go, if it finds it. So the next thing that I want to talk about is it does do some health checks on your tests. For example, flakiness. Like if a test tends to sometimes fail, but sometimes also pass, independent of the input data. Like, I don't know, you have an unreliable database access or something like this. Hypothesis will try and find this. I've simulated this. I mean, I've tried with the random module, but turns out that this is actually not so easy to make hypothesis to make flaky tests based on randomness, because hypothesis does some clever things about seeding the Python random number generators. But I simulated this with the nano system time. Yeah, what it does here is basically it finds a failing example, in this case here 0, 0, and then it just goes ahead and says, you know what? This failed once, but what if I put it in again? Oh, it passes now. That's bad. And it actually tells you in the stack trace somewhere here there will be the hidden message that actually your test is flaky. And you should do something about your test before I can actually tell you what the bug is. So what if you're not satisfied with the built-in strategies? Like, for example, I can generate dates. But what if I want to actually have dates that are only Monday to Friday? And what if I want to have these dates in a string representation? Well, I can easily do that. I take the base strategy. I can apply a filter, which gives me back another strategy, but containing only values that satisfy the predicate. In this case, like only Monday to Friday dates are allowed. And then I can map this to a strategy that produces actually the ISO format representations of the generated data. And there's even a interactive kind of filter that you can apply in your tests. Like, some things about your test data you only know within the test code, and in this case I've simulated this here. Like, if I get this test data and for some reason this date contains a 9, then this is not a valid test input for my function. I want to exclude that, so I take the assume function, the hypothesis built-in assume function, to actually exclude or skip all the tests where a 9 is in my input data. So if we have a look at this, I mean, I can't from the top of my head verify that all of these are not Saturdays or Sunday, but I can see that none of these actually contain a 9, and that it like created a lot of ISO format dates. Weird dates, actually, but valid dates. And like you might say, what if I have something like, what if I have data that has interdependencies? And also that is possible. Hypothesis does have a workaround called the data strategy, which doesn't actually generate stuff itself, but it gives you a draw function, like draw not in the sense of pencil and paper, but draw in the statistical experiment sense, which takes a child strategy and then interactively produces sample data from that with all the same magic that happens around hypothesis tests in general. In this case, I have an example where you first draw a lower bound integer and then an upper bound integer that is above the lower bound, and then another value that should be in between. And this way I can avoid a lot of assume statements, because in the end, if I choose to exclude too much test data, then hypothesis at some point will start and complain that it's not actually easy for it to generate a lot of data fast and that the test is probably unreliable. So yeah, this is the way to go if we want to have interdependencies in our input data. And if we run this, then we see, yes, actually these properties are true. Lower, midpoint, and upper bound are actually have the properties we want. So what now if I actually have data transfer objects or classes or so? Like, can I still test that with hypothesis? I mean, integers and strings and stuff are great, but I mean, I have users and whatever, blog posts, to-do notes. But actually, hypothesis is pretty clever about certain built-in data types and even data classes and pydantic base models. In this case, I've chosen a pydantic base model. I've created an enumeration with some Python skills, Python testing skills in this case included, for example, hypothesis. And I've created a Pythonista class, which has an ID, a name, an optional age, which should be at least 0 at max 200 years, and a very particular set of skills, like hands up who actually knows the movie referenced here. And I have a domain logic class called Meetup, which has a list of signed up people, Pythonistas, and you can actually reserve a spot in this meetup by adding a new member to it, and then also in the end get the number of reservations for this meetup. So a test for this could look somewhat like this. I let hypothesis generate a list of Pythonistas with the from type strategy, which magically infers how a Pythonista could be generated, and someone new that wants to join the meetup. And then in the test, like as usual, I initialize my meetup with the initial visitors. I check how many reservations I had before. I sign up someone new, and I do a property-based check on the number of reservations. They should have increased by 1 if someone signs up. And in particular, this shouldn't raise any unexpected error condition. And if we have a look, I mean, clearly this test passes. It's not so hard to see that the implementation was actually correct. And we see here, yeah, hypothesis is well able to actually create this complex domain data transfer object with, like, as if I had generated all of these properties individually, and it even can do UUIDs magically. I didn't tell it how it can do UUIDs, like it was just built in. So as I said, hypothesis is pretty clever about a lot of data types and can actually generate these. Yeah, so let's go back to the slides. As a quick summary, how do you use hypothesis in your testing code? Well, things that you should and could do. Probably one test per property. Like, don't try to test multiple properties at once. It won't make you happy. You should write these kinds of tests only for simple units, usually, or integration tests that are really, like, that can be overlooked really easily and do simple enough things. It's not usually meant for very long running or very complex tests, because then quickly hypothesis will start to complain that, like, it can't actually properly test the stuff that you gave it. Good candidates are stuff like pure functions, like functions that don't have too many significant side effects, like, I don't know, printing or logging is probably okay. Modifications in the database, sending an email, firing a rocket, probably not so well testable with hypothesis because it just rapid fires input data into it. Functionalities that round trip, like if I have a date and I can dump it to an ISO format string and I can pass back that string to get back a date, maybe it shouldn't alter the original date, like I get back the original date if I do that. Or if I store something into some format or database and I load it back, hopefully it isn't modified afterwards. Or functionalities that compose naturally together. For example, like if I sort something in reverse, then hopefully it's the same thing as sorting it normally, but then reversing it afterwards. Like, these compose and can be tested against each other. And if one of these functions breaks, I will notice in the test. Or fuzz testing, like you generate lots and lots of input data and you put it into your function. You don't really care what happens with this data and what comes out, but what you do care about is that it either succeeds or throws an error that you expect, but nothing unexpected happens. Like, say you have a very simple endpoint and you put a lot of input data in and you don't want to have server errors, like authentication errors, 404, all of that is fine, but no 500s. Stuff like that would be possible. What you shouldn't probably do with hypothesis, like try to test everything this way. I've already given you that word of warning. It's pretty easy to miss important properties, and like it doesn't hurt if you like add one or two additional example-based tests for everything that you want to use in production. And it's also pretty easy to confuse properties with implementation details. Like, everyone had this experience. You change something about your functionality, like in the end it kind of does the same thing, but does it slightly differently. Still 2 or 3 tests break. And then in the end you realize that what you actually tested was not a black box, but you actually tested how the implementation was working, and this is annoying. And like, property-based testing doesn't save you from that. It's easy to confuse properties of an algorithm with how the algorithm is implemented, just as a warning. Basically, like, you should never try and test implementation details, but as I said, it's hard. Yeah, I already said that. Don't forget to just add 1 or 2 handcrafted example-based tests just in case you missed any of the properties. And then, final warning, you shouldn't expect hypothesis to always find edge cases, and even the rarest edge cases, in brackets, immediately. Like, hypothesis does the following thing. It does have a cache. If the cache is there, it remembers a few successful examples from the last test run, and it retries these, like trying if anything about these examples is now breaking. Then it has a random portion where it actually generates new data. And if it finds a failing test, it definitely also remembers the failing examples to retry these next time, to be sure that maybe they got fixed or that they are still failing. So the random exploration is actually only, like, I suppose, about half of the testing. And if you had like a function that only fails if one parameter is exactly the number 1000, then it's pretty unlikely that hypothesis will quickly come up with exactly that one example that makes the test fail. But on the other hand, it's pretty unlikely that you actually implement such a thing that only fails for one very rare exotic case. Like usually things fail for edge conditions, like 0, empty lists, numbers above a certain threshold, and so on. And for that, hypothesis again is pretty good at finding these things. But don't expect that if you have a very rare bug that hypothesis will actually find it very quickly. It eventually may. And there's a lot more to say about hypothesis, but I won't bug you with that. For example, you can register type strategies. If you find that hypothesis can't actually generate a data type that you have, you can write your own strategy to fulfill that. You can write your own custom complex strategies. Like you can even implement recursive strategies that generate recursive data structures, like for example trees and graphs. And there's even a command line tool on its page that can ghost write tests for functionality. I have no idea how it works. I have no idea how well it works. I've never tried it. I just wanted to mention it here, that there is a command line tool that can like even write blueprint tests for you. And so on and so forth. So if you want to have a look in detail, then the best entry point is actually just the documentation of hypothesis. So that's the end of my presentation. I've had even more overtime than in the original live talk, but I mean, never mind. This is now offline. Let me think about questions that were asked in the live round. One question was kind of related where hypothesis comes from, and my answer was something along the lines of, this is from the functional programming community. Tools like this that do property-based testing and that do systematically generate data for tests, they come from originally, I think, Haskell. And there is a popular Haskell library whose name I just forgot, that is kind of like the inspiration for hypothesis. And I think it's awesome that someone actually took this idea and ported it over to Python and gave us this gift of hypothesis. Yeah, I think another question was about determinism, and my answer was along the lines of, hypothesis does have this database, this cache of examples that it tried before, but also this random portion where it tries out new things. But there is a possibility to set via settings a seed for the data generation, which makes it more deterministic. And I added another caveat: if you use hypothesis in a CI pipeline, then you should remember to actually persist the hypothesis cache directories. Like if you forget to cache these and the container is discarded afterwards, then the database of hypothesis examples is gone. So you should take a bit care to configure your CI pipeline correctly, such that hypothesis is properly seeded and properly persists the test example database. And I can't actually remember anything else from the Q&A round. Yeah, anyways, if I end up uploading this to any channel in the near future, then sure, you can like ask a question in the comments or just have a look at the official documentation of it. And for the sake of completeness, I've borrowed the images in this presentation from either my own phone or from these URLs. I hope that's legally enough to not get to jail. Anyways, thank you for listening if you made it until here. Sorry that it's not the original live recording, but I don't know what happened. It kind of broke, and hope you found it useful and interesting, and join me in actually writing more property-based tests, because I think they're awesome and they help you a lot engineering your stuff. See you soon. Bye bye.